Hi everyone and welcome back to the series called AI Concepts with Coding from Scratch. In this tutorial, you will learn how to implement the two most popular machine learning algorithm, linear regression and the logistic regression. We are going to building each and every algorithm from scratch without using any library called Scikit-Learn, TensorFlow or PyTorch. This is the first video where I will deploying here the two machine learning algorithm and the rest of the algorithm is coming soon. If you want to learn Python, data science, machine learning and GenAI, subscribe my YouTube channel. So today we are going to discussing about the linear regressions and the logistic regressions, and we are also going to implement this one from scratch. So what is the linear regression? Linear regression is the most easiest and the most popular machine learning algorithm. This algorithm shows an linear relationship between the dependent and the independent variables. And you can see here this is a graph, and here you can see here one best fit line. It's called a best fit line, which one actually calculate the loss of the each of the data point. And this is the equation for that. We having y hat equal to wx plus b. Here w stand for weight and b stand for biases. Okay. In the mathematics, you have one equation for the straight line called y equal to mx plus c. Here m is stand for slope and c is a constant and y is the intercept. Well, so this is the same formula that you're going to using it here for solving the machine learning problem. While you are set up here your best fit line in your graph for your certain data point, you may get some kind of error. That's called the error in the linear regressions, or you can say the loss in the linear regression. For calculating the error in the linear regression using here a formula called MAC, also stand for mean squared error. So this is the formula for that, for the mean squared error. So what we having 1 by n, and we having the y minus y hat. Where y is nothing but our true value or the actual value, and y hat is nothing but the predicted value by our machine learning model. In the graph section, you can see here one thing. We having one best fit line, and you also having certain data point you can see on here. And this is nothing but the distance of the data point. It's also called the error. That's mean how far or how close our data point from our best fit line. If we got here the best accuracy, our best fit line should be go up, down like that. So one more thing, I don't have any iPad or the tablets so that I can draw it down. I just using here on pen and paper and try to write it down and take a picture using my mobile phone, and I set it down in the PowerPoint presentation. So that's my effort. I cannot actually afford to buy here one iPad or tablet, so that's why I using here my own method here, pen and paper. The best idea to do that. Okay, that I think. So for calculating the error using here this MAC, that's the formula for that. And in here, are we actually using here the derivative of that? Because see, in the case of machine learning and the deep learning cases, we can go here, use here one forward path, and you're also using here a backward path. So in the case of linear regression, backward path is not happening because it cannot calculate the gradient well in the case of non-linear data, but it can also calculate the gradient in the form of linear data. So that's why linear regression is used in the case of linear data, not the non-linear data. In the non-linear data, it's not unable to capture the data well. See, in here we are actually using here the same formula in here, and we make it as a z of wb, just giving here one name, and then we are going to passing here the same below on here just for the y hat. I mean wx plus b, same thing. And after that we can do the derivative of this formula. So for the derivative of the formula, I mean for the calculate the gradient, we are using here an most popular optimization algorithm called the gradient descent. Called the gradient descent. You can see on here gradient descent. Okay, this is the optimization technique. Optimization technique. But just go the before slide. So what you have, we need to also do some kind of optimization on here. You can see here we have our formula, and if we do the derivative of that, derivative of this thing, what we getting here this one minus 2x, we having on y, and we having wx plus b. If you don't know that how the calculus actually work, how the differentiation and how the integration actually work, you are unable to learn the machine learning. It also having the knowledge about statistics, you have the knowledge about the algebra, you have to knowledge about the calculus. So you can see here for the simplification purposes, I actually using this one, and you can see here df by dw. It's not f, it should be the j, by mistake actually writing down here. Then we are going to using here this one, so 2 should be coming on here with respective weight. We getting here this formula. We getting here this formula, and for the biases we getting this formula. See, both of the cases we have the minus, and both of the cases we have the 2 and the 2. So while you do the coding, you're not going to using this minus sign and the 2, just because of we can removing this one because it's same in the each of the cases for the weight and the biases. Okay, so now what I can do, I'm going to go to the next slide. That's our optimization algorithm called the gradient descent. So in the gradient descent, we having one initialized weight, higher you having a parameter, or you can say the weight, and to slowly go down and try to reaching here our global minima point. It's called global minima point. So it's called also called the global cost minima. Higher you need to minimize the cost, or higher you need to minimize the loss. And this is called a gradient. See how the gradient actually look like. It's a derivative for that. Now you can see here we're using here formula for updating the weight and the biases. That's the formula. Weight equal to weight minus learning rate, important term, learning rate, and then we have the derivative of the w, I mean the weight. So what is the learning rate? Learning rate actually tells us how quick or how slowly you can reach to this global minima point. That's the use of the learning rate. If you are using here two learning rate, it will go into the global minimum point slowly, but it will give you the output, but it will take much more amount of time. Just right, if you're using here the best or your good choice of the learning rate, you can go to the global minimum point in a just right time. But if you are using too high learning rate, it will keep jumping here and here. Okay, but it's not going to reaching here your global minimum point. It's not unable to optimize your algorithm, and you get here one worst or so bad machine learning models. Okay, so you can see here how can actually update the biases at all. Now let's go on the next slide. So you can see that how can you update the parameters, and you can see here that's our formula, I mean for the derivative, and you have one simple formula for that. Okay, and we also back down to it officially, I mean these cases. But let's try to checking this one. This is nothing but our updated parameter, that how can you update the parameters while we calculate the dw and the db while you do the coding. Then you can also see this one. See how can you do that. If you're taking one pen, just taking one pen. So that's our formula. You can see here we can writing this one as a 1 is nothing but about 2, it's nothing but for the weight, and this is nothing but for the biases. You can see here we have a 1 by n and summation of I equal to 1 and n and 2x dot product of y hat minus y1. But in here you can see here y is nothing but and the first. But here you can see here y is nothing but go to the down, I mean the last person. So what actually happening here, that try to taking the common from here. I mean if I writing this formula like that, let's say yi minus y hat, I mean, I'm just going to actually replace this y wx plus ib is equal to y. So we having this one, right? We having this one, also we having the minus. So if we're taking the common, the minus common from here, what you have, we having common for that. So we having minus 1 into minus, then we having the y hat, and minus of y I. So minus minus equal to plus. That's been positive. So we got in here y hat minus yi like that. That's why this formula is coming in here in these sections. So you're having this one, we're simply going to replacing this minus sign from here. I mean minus into minus is actually positive in this case, because we're going to writing this minus here. This is nothing but this one, and we're having this one. Okay, so that's why minus minus equal to positive, and is nothing but minus is gone. And you got in here one simplified version of formula for updating the parameters. Okay, because I don't have any pad, so that's why I'm able to using here this mouse again. Okay, so let's try to removing this all of the things because it's look ugly, and try to taking the highlight again. So you can see here, let's try to break down it efficiently. So you have a formula called w is equal to, I mean y hat equal to wx plus b, And if I do the predictions, you need to using here wx plus b. I mean, x is nothing but the features. So while I do the coding, you're actually using here this x is a capital and y is a small cases. So x is nothing but our features. This is nothing but an independent features, and this is nothing but a y. Y is a dependent features. So you're having multiply with a weight. So we got in here wx1, wx2, and up to n, because number of features can be multiple. And after that, what I can do, you can using here the y predict, and you can do simply going to replacing the x value inside that. Okay, inside that, inside that, inside that, inside that. Now the most important thing here, see, we do the transpose of the xt. Why? See, if I see that it's this equal sign is not here, just by mistake. By mistake, to do it here. It don't have any equal sign on here. So you have the value for the y prediction, which is called the wx1b, wx2b, wx1 up to b, and this is nothing but our dw. So why this xt? Because see, why or do the dot product of that, the size of the dimension of the matrix should be equal. But in here, you can see that this dimension is actually equal on these cases. So you cannot do the dot product of each of the features. You cannot do that. So that's why you need to do the transpose of the xt. While I do the coding, you can also see this out. Okay, this is how you can update the parameter. This is how you can actually break down it efficiently. Now what I can do is simply going to implementing these linear regressions using Python without using any module called Scikit-Learn. So you're already creating here a folder called linear regression, and already creating here a file called model.py. So first what I can do, we're going to importing here the numpy. Let's say importing here numpy as np. Then we're going to importing here matplotlib.pyplot. Let's say matplotlib.pyplot as plt. If you don't know that what is the numpy, what is matplotlib and the pandas, just go on my YouTube channel and search for Daredevil Python data analysis library. Just go on here and learn about the pandas, matplotlib, and the numpy, right? So now what I can do is simply going to create a class called linear regression. So let's say class linear regression, and then we're simply going to using his dev, and we having the init, and we're going to passing here the self. Then we're going to passing here two things. One is called the learning rate. Let's say learning rate is equal to 0.01. We give it here the by default value. Then we're going to passing here the iterations. Iteration is equal to, let's say, 1000. It's nothing but one epochs in the neural network, like that, because you need to do the updation of the parameter or the weight and the biases. Then after that, what I can do is simply going to initialize this value. So let's say self.lr is equal to learning rate. Then we have the self dot iteration. Let's say iterations is equal to iterations. Then after that, what we have the weight and the biases. Let's say self dot weight, and weights is nothing but our, let's say, none. Okay, so by default, I'm going to making the weight and the bias, it should be none. And after that, you can giving here some of the random value, and we also do the updation of the weight and biases. So let's say self dot bias is equal to none itself. Okay. Then after that, we can actually adding here one list for losses, so that we can also see the loss, that how can a loss is calculated, and for the each of the iterations. So we're also creating here a list, empty list for the losses as well. Now what I can do is simply going to creating here one function that's called the fit, that you see in the scikit-learn. But in here, we are not going to using here any module called scikit-learn. So that's why you need to do it manually. Okay. So what you can do is simply going to give it here the fit, and then you're going to passing here the self and our dependent and the independent feature. That's our independent and the dependent feature. Let's pass it this out. And after that, what I can do is simply going to creating here one for loop. But before that, it also starting here the number of feature and the sample, because in our updation parameter or the calculating the error, we basically using here 1 by n. Higher n is nothing but our sample. If I go on the slide again, then you can see here it's having 1 by n, and higher n is nothing but our samples. So how can I get the sample? We can get the sample from the x, I mean shape of the x. So if I go on here, so how can you do that? You can using here x.shape. Then you can simply going to go on here. You have the number of samples. Then you have the number of features. Let's say number of features. Okay, that is how we can getting here the number of samples and the number of features. I mean, how many features we have. Then after that, what you can do is simply going to initialize the weight should be the zeros and bias should be the zeros, because weight is nothing but one vector. So what I can do, you can using here self dot weights is equal to np dot zeros, because this is one vector. So you can pass in here the number of feature, because based on the feature to give it here, initialize here, all of the features should be the zeros. And here for the biases, we can simply go into using here bias is equal to 0.0, like that. So it should be bias like that. Now we can simply go into compute the gradient and also update the parameters and update the loss function as well. So what I can do, we simply going to calculate the gradients. So we have the certain iterations. So what I can do, you can using here for loop. Let's say for I in range of the iterations. Then after that, it should be self dot iterations. So it should be self dot iterations, and then inside that we can do the prediction of that. If I go on here, if I go on the slide, you can see here you have a value called wx plus b, and w is x is nothing but one dot product. So how can I do that? We can using here np dot dot, and inside that you can pass in here x and self dot weight, and then we can using here plus self dot bias, same thing you can see here. And this is nothing but our y prat, you can see on here y prat. So what do you have, we have this y prediction, like that prediction. That's our y predictions. Then what I can do is simply going to calculate the dw and the db. If I go again, you can see here we're calculating this dw and the db. So let's calculating this one. So you have in the dw, this is called the compute the gradient or gradient descent. I mean, calculating the gradient for that, derivative for the gradient का मतलब है क्या हुआ, डेरिवेटिव करना बस, अरे हिंदी चला है बस. Okay, dw, then what I can do is simply going to using the formula called 2 by number of samples into np dot product of the x, see x dot t transpose c. Why? This t is nothing but the transpose of that. Now why 2 is coming here, if I do the derivative of that, this formula is also look like that. You can writing the formula like that, 2 by n, and the summation of the I equal to 1, and you have the n, then we can writing this on like this way, y hat minus y into x, like that. And here x is nothing but the transpose that you can see on here, right? So let's go on here, and then you can simply go into give it here y predicted minus y that is coming from here. Okay, this is how we can calculate the dw, and dw is nothing but the dot product of that. Now biases, it just added. So what I can do, you can using here db equal to, we can using here the 2 by number of samples, it's a number of samples, and then you can using here this one, we can using an np dot sum, because this is a dot and this is sum in the weight, so biases, and you have the predictions minus y. So for the derivative of the weight, we actually using the dot product, and in here in the sum, we actually do the summations for the biases. Now we need to calculate, we need to update the parameter, right? We need to update the weight and the biases. So how can I update it out? So you can using the self dot weight. You can self dot weight is equal to, weight is nothing but this weight is nothing but our new weight. So you can using here the weight minus learning rate, let's say learning rate lr, or learning rate lr, so it should be self dot lr. So let's say self dot lr, that is simply going to into it dw that we calculated on here. If I go just back, you can see that how can you calculate this one. This is called weight is equal to w minus learning rate of this one. Okay, just I'm going to follow in the slide, right? Then you have the self dot bias is equal to self dot bias minus self dot lr into db, right? Like that, because you need to calculate the bias itself. That's it. Now how can I update the parameter? Now we need to calculate the loss. We need to calculate the loss. Now how can I calculate the loss for this value? How can by using the MSE. So for that, we need to also creating here a function for the MSE. So let's say def compute, or you can say let's say MSE like that, MSE. So we can pass in here the y true and the y prediction, because error is nothing but the how difference between, or I mean how many errors between the actual value and the predicted value. So what I can do is simply going to first calculate the number of samples is coming from here. Let's say number of samples is equal to length of y true, and after that we need to calculate the MSE. So let's say MSE. So how can I calculate the MSE? If I go on here, and this is the formula, 1 by n equal to a summation of y minus y height whole square. So what you can do, you can using here np dot sum, because this is summation, you can see on here summations. If I do the derivative, it's not coming on here, because while I do the derivative of these summations, it's not here. Okay, it's not here. We are not going to using it in the coding part, but in the calculation of the MSE, you need to using here this formula. Okay, so np dot sum, and inside that what you can do, you can pass in here this y true and the y true minus y prediction. Let's say y predictions. Then you can using here this 2. Okay, you can give it here y prediction first, because if we do the square of that, it means the negative is equal to positive. Then after that, you can divide them with the number of samples. That's the number of samples. That's it. Okay, so we can got in here the MSE, and it also returning this out, return here the MSE, and now it's simply going to using this in this section for computing the losses. So we can using here, let's say loss is equal to MSE, and you can pass in here the y and the y prediction. Let's say y predictions. And after that, we can simply going to add it to the losses. If loss is equal to self.losses.append, we can pass in here the loss itself. Cool. Now we have to do one thing called the predict, that you see in the also scikit-learn. Let's say predict, and we pass here self and x. So the predictions, what we have the our calculated weight and the biases, because after doing the gradient descent, I mean the weight updation, we having one single weight and biases. So we're going to return this out. Let's say I'm going to returning here this np dot, and you can returning here this x comma self dot weight and the biases. Okay, because after each of the iteration we're having this weight and the biases value. Now we can simply going to uh, actually getting here some dummy value and try to testing this out. Let's say x is equal to, let's say I'm going to giving here one np dot array. That's array, and inside these sections we can getting here a list of list, and inside I'm going to give here one, let's say two, let's say three, three, and let's say give it here the four. Okay, just for testing purposes. And I'm using here on y, and y is nothing but our independent features that you need to predict. Let's say array, and you're going to passing here, let's say 2 4 6 8 like that. And then you can using here this model is equal to linear regression. We are not using here any scikit-learn module. You can passing here the x, not x actually, learning rate. Let's say 0.01. Then you have the iterations. You can change the iteration on here. Let's say 1000 you have. You can give it here, let's say 2000. And then after that, you can do the predictions. Let's say model.predict. I mean fit. It's a model.feed. And then you can pass in here x comma y. And then you can do the prediction. Let's say predictions is equal to model.predict. And you can give it to here x. Okay. And after that we can print the prediction. Let's say prediction, and then you can compute the loss as well. You can also see the loss from here. Otherwise you can also using this model to getting the value from the losses from here. So how can you do that? You can have the loss variable, and you can using here model dot losses, because it's also have the losses, and now you can print the losses as well. Let's say loss, and you can simply go into printing without loss in the f string. Then you have the prediction as well, so we can also printing this out. Let's print here the prediction. Let's say prediction, and we having this one predictions, and you can simply go into using this f. Okay, so you can in this loss sections you can get all of the value as a list, because this is passing here one list of the value. So what you can do is simply going to saving this one, and I'm going to running this one. So you have the 2000 iteration. Obviously, it will taking few seconds, and our data is quite low. So see, we having the loss of 0.002 at the last loss, because we calculate the last loss, and the first time we got in the loss of we got in the loss of maybe we get the loss of the 30 starting from 30, and these are predictions 2, 4, 5, and 7 is the predictions, but we give it here 2, 4, 6, 8, and 2, 4 we got in here 6, 5, 7, but we give it here 6 and 8. That's mean that's the loss, and that's the error of that. Okay? This is how it can calculate it. Now what I can do, we can simply go into do the curve for this loss curve. So you can using the matplotlib, and you're already importing this out before in here. So we can using here style, let's say plt.style.use, and the next one is called the logistic regression. You're going to actually using it, I mean, we are going to coding it out in the Jupyter notebook because it's quite annoying in this BS code. Okay, let's say 5, 38, 38. So next of the algorithm should be recording it in the Jupyter notebook. It should be better. Okay. So what I can do, you can simply go into plotting this out. Let's say plt.figure, and you can give it to here the fixed size. Let's say 8,5, and you can give it here plt.plot, and inside that you can pass in here model.losses, and then you can give it a level. Let's say MSC loss, and then what I can do, you can simply go into giving your title. Let's say plt.title, and you can give it a title called, let's say, loss curve, and then I'm simply going to give it here plt.x level, and this is nothing but our iterations. Then we have the loss. So let's say plt.y level, y level, we can passing here the loss. Then you have the plt.show, like that. So now we can run in the code from here. So you can just go on here and click on run the code, or you can also go on the terminal section, and you can also run in this one. Now you can see here we can giving here some of the predictions, as well as we got in here on loss curve, because we're going to plotting this out, and you can see that how gradually the loss is decreases. You can see in the sections, but the loss is not actually visible quite okay. I mean, you cannot see it correctly, but you can see here this loss is nothing but from 30 to it will gradually decreases up to 0.222, like that. So now what I can do, I am simply going to adding here one more thing, just adding here some of the random data, just like the real estate, and try to predict it out and try to see the loss curve for that. Okay. Okay, so that's the code. I first import here pandas. Then from scikit-learn.model selection, importing here the train test split, because this is one kind of machine learning task. And you also import here the standard scalar. So I'm not going to discussing about this thing, the train test split, the standard scalar, because we are not building it yet. The loss or the scaling or the standardization or the normalization takes. So that's why I'm just simply going to import it here just for testing purposes. I'm not going to actually discuss about the code, okay, on here. Just I'm going to see about that, how actually do the prediction and how the loss curve actually work. So what you actually do is simply going to creating here one sample of the real estate data. Then you create it one data frame for that, and we actually divide them for the dependent and independent features, because in here you can see here passing here the dependent and independent feature as well. Then after that, I am simply going to put it inside this standard scalar. I mean, for scale the feature or normalize the feature, so that our machine learning can actually understand the pattern of each of the data point. Then we have the split data, because in order to overcome the overfit or some kind of problem in the activation function, so that's why I need to also train, test, and split of here. Then after that, is simply going to using here this linear regression that you actually created, and we passing here the learning rate and the iterations, and you have this predict and also the predictions, and also you can see the predictions. You have the loss, it print the losses, and also the figure. Okay, so you can removing one prediction from here because it's not needed at all. It's duplicated. So you can simply going to running this out and see the output. Just for seeing the output, I just actually pasting here the code. And this is for the first one, the first loss curve that you can see on here. And the second loss curve should be appeared. Just to wait for a few seconds, it will appear the loss curve for the second one. And you can see here, it's actually creating some random data. You can see here, now you can see the loss is how the loss is gradually decreases. And you can see here the value is nothing but started from 3.5. Value for the weight and the biases, right? You can see on here. So how you can see the loss is decreases. So now what I can do, we're simply going to creating here our next machine learning algorithm called the logistic regressions. So in the linear regressions, you can see here using here this MSE as for the calculating the error, and also using here the gradient descent algorithm, the optimization algorithm for optimize that actually accuracy or the value. Okay, and you're also using here some of the dot product on here, weight and the biases. So now let's go on the next one that's called logistic regressions. So in the list, our next machine learning algorithm is called the logistic regression. So this is one popular machine learning algorithms, just like the linear regression. Just in the linear regression, we solve the data which one is the form of linear. But in the logistic regressions, it is nothing but used in non-linear data. And this logistic regression is also similar to the perceptron in the neural network. In the logistic regression, they're using here a term called the sigmoid activation function. If you don't know what is activation function and how to use that, you can check out my videos about the activation function in the AI concept with coding from Scikit series. So in the sigmoid activation function, it having one maximum value of the 1 and minimum value of the 0. That means the range is between 0 to 1. And in the middle, you can check here the threshold value is nothing called 0.5. I mean in the sections. And you can see here we're having our formula y hat equal to wx plus b. Here W stand for weight and B is stand for the biases. And this is the formula for the sigmoid or the logistic activation function. So in linear, we're actually using here the linear activation function, but it's not using it here in our linear regression. But in here, logistic, we're using here a non-linear activation function so that we can also classify the non-linear types of data. So that's our formula, 1 divided by 1 plus e to the power x. Now let's go on the next slide and see that how can we calculate the error. In the calculating the error for the logistic regression, you can using here the binary cross entropy. So this is the formula for the binary cross entropy. And also one more thing, just for clarify that, that's our formula for the sigmoid activation function. And then we're simply going to using here this formula inside our formula, this yx wx plus b, and it got in here formula like that. So 1 divided by 1 plus e to the power minus wx plus b. That's mean instead of using the x, we're simply going to replacing with the value of the y. And this is nothing but our y hat that you can see on here. So y hat is nothing but our predicted value. Now I'm simply going to actually initialize this one as a formula called h theta x, so that we don't need to write it more on here, just giving here a symbol. So in the case of cluster regression, we are using here a formula for the calculating the error that's called the binary cross entropy. Okay, you can see binary cross entropy. So this is the formula for the binary cross entropy. You can see here 1 by n and summation of I equals to 1 minus y log. See, we're using here the log. It's also called the log loss. This binary cross entropy also called the log loss because it using here the formula in the format using here the log. Then you have the h theta x plus 1 minus y log of 1 minus h theta of x. That means you can see here we having one portion, this portion, and we have the another portion for 1 minus y. So we can define it in the code. It's nothing but on y1 or it is a y2. Then after that, we can join them and we can take in the mean for that. This is the mean for that. And this is nothing but for the cross entropy and for calculating the error. Now, how can you update the parameter and how can you calculate the derivative of that? Derivative means the gradient. So to calculate the gradient, use the formula called the, optimization technique called the gradient descent. Okay, because using gradient we can actually update a parameter and we can optimize our logistic regression algorithms. So this is the derivative of the weight and the biases based on here. You can see here weight and the biases, and we got in here the same formula that is written on here in the linear regression. If I go back, you can see here we're writing here the same formula for the linear regression as well. You can see on here. Okay, And then how can you actually update the parameter? We can update the parameter in this formula. W equal to W minus learning rate, or you can say alpha, minus dW. Then you have the bias, and B minus learning rate of dB. So higher alpha is nothing but the learning rate. And you can see here, this is the gradient descent algorithm that you can see earlier. We having one parameter, or you have the initialized weight, or to go down, 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 and until we reaching here our global minima point. Okay, so we have the some kind of graph. If it is too low, it will taking much more amount of time. It is just right, it will give you the optimal solution. Or if it's too high, it will keep jumping over here and there, but it's not going to move inside our global minima point. So this is the technique that you can using here for updating the parameters, in the gradient descent. Then you're having this one, breaking down it efficiently. You can using here the same thing, because it's also same as the linear regressions, but just having one problem, it will actually using here on non-linear activation function. Now what I can go, we simply going to actually implement these logistic regressions. So let's go on here and try to implementing here the logistic regression. So for this case, we're going to be using here the Jupyter Notebook, not VS Code, because Jupyter Notebook is the best choice in order to building any machine learning model or coding for the data science. So first, what I can do, I am simply going to importing here the NumPy, because it's needed in order to do the dot product or any kind of multiplication. So I'm going to first importing here NumPy as NP. Let's say NumPy as NP. Then after that, what I can go, I am simply going to actually creating here a class for the logistic regression. So let's say create a class. Let's say logistic regression. Let's say regression. That's it. So you have the class called logistic regression. Then after that, I can using here def. So it's better you can running it again so that our warning is gone. So let's say def, and you're going to using here init. Then we're going to passing here self comma learning rate. Let's say learning underscore rate is equal to, let's say, 0.01. Okay, more higher learning rate, it will jumping over here and there. It's not going to the global minimum points. And after that, we can giving here the number of iteration. Let's say iters. So let's say I'm going to give it here the 1000s. You can give it up to that. It's nothing but a default value. You can also passing it here as a parameters. And then we're going to initialize this one. Let's say initialization. And what I can do is simply going to define it and initialize this one. So we having this section over there. Okay, so we can removing this one, and after that we can go on here, because it's not it going here, that's because of I actually do one comment. So that's why. So we can go on here just using here one tab, two tab, then you can go on here. So what do you have? We have the self dot, we have the learning rate, then we have the learning rate. It's coming as a parameter. Let's say learning rate. Then it's again going. It's better we can just removing this one, and you can simply go into using here one hashtag on here, because I am using here a shortcut technique called control and the backslash. That's why it will actually creating here the comment section, comment line in here. Okay, don't do that. So then I'm going to using here self dot number of iterators. So let's say iterators is equal to nothing but number of iterators. Okay, it's just like epochs. So let's say self dot weights. Let's say weights is nothing but our nan. Then I'm going to using on self dot bios is equal to, let's say, learn or nan, whatever. That you have the self dot losses. So let's make it as a empty. Then after that, we're simply going to define here our sigmoid activation function in the logistic regression. So we're going to using here def sigmoid, and then you can pass in here the self and the x. Okay, so this is nothing but our x is nothing but the independent variable, because it's not dependent to the y and the axis changes and y is also changes. Then we're going to return here, let's say return here 1 divided by, okay, 1 divided by, this is formula, 1 plus np dot exp of minus x. This is a formula for the sigmoid activation function. If I go to the slide again, then you can see we have the formula called 1 by 1 plus e to the power minus x. Okay, where x is nothing but this one, these equations. So you can go on here, and then we implementing here our sigmoid activation function. Now what I can do, we can simply going to compute the loss. So let's say compute the loss. So we can give it here two value. Let's say self of y true, and we have the y prediction. Let's say y prediction. Then what I have, we need to using here the formula for the computing the loss. So you have the formula. So you have the formula for the compute the loss. So this portion I'm going to taking it as a y1, and this portion I'm going to taking one as a y2. Then I'm going to taking the mean value from here. Okay. So I'm going to go on here, and then we have the y1 and the y2. Let's say y1 is equal to, it's nothing but our y2. Then we're going to using here dot, I mean the, it's called the multiply sign. Then I'm going to using here np dot log. That I am simply going to give it here y predictions and the epsilon. I'm going to giving here one parameter called epsilon. Why epsilon? Just because of when you computing the loss, if the loss is going to the zero, it's not going to compute it, this one. It will give you some kind of error. So that's why you can give it here one some kind of a big value. So you can give it here epsilon. I mean, not big value actually, lower value. Let's say y e minus 9. Okay. And after that you can give it here the epsilon. I'm going to passing it here epsilon. So you know that what is the y true and the y predict, because you already know that how the linear regression actually work, and how can you got in here the actual value and the predicted value. Then we have the y2. We have the y2. So we can making it, let's say 1 minus y true. Then you're going to using here same technique, I mean same thing, just instead of using the y predict, we can using here 1 minus. Okay, let's say 1 minus y predict like that. Okay. Then we need to do the mean of that. So we can returning here, let's say return here the minus of np dot mean of the y1 plus y2. That's it. So how can I compute the loss for here? Now we can fit it out, because in a logistic regression, I mean the scikit-learn, we have one method called fit. So you're not also creating this method on here so that you can also fit with the data. So let's say def fit, and you can passing here self comma x comma y, and then we're simply going to start in the feature from here, because in the linear regression for getting the samples on the feature, we're using here the same code that you can see on here, same code using it here, number of samples and number of feature as the x dot shape. So what we can do, we can simply go into actually using here this x dot shape for taking the number of samples and the number of features, and after that we can initialize the weight and the biases of the zero. So you can copy this code from here as well. So you can copy this code from here as well, and you can simply going to paste it here, because these lines of code is almost same. And after that, what I can do, let's take in some shell so that you can stall it out, and then we can simply going to creating here a for loop. Let's say for I in range, and we are going to passing here self dot number of iterators. And then what I can do, we are simply going to predict it, because first time when you are going to do it, because logistic regression is also same like as the linear regression, just it having a different that it will pass in the data, or it is pass in the value or the prediction inside one sigmoid activation functions. So what I can do, we can simply go to using here this np dot product of the x, and you have the self dot weights. Then we can simply going to adding here self dot bias. That's it. And after that, what I can do is simply going to store it inside a variable called linear prediction. See, these our linear predictions. So we can get in here np dot product of x and self of weight, I mean weight into x, then you have the self dot bias. This is the formula for the linear regressions. Now we're going to pass in this linear regression inside one sigmoid activation function. Then our logistic regression is actually built it. So you can pass in here sigmoid, and then I am simply going to passing here the linear prediction. Let's say predictions. That's it. And that's our predictions. That's our predictions. Now we got our predictions. Now what we need to do? We need to calculate the gradient for that. I mean derivative for that. But before that, let's try to add here our losses. So let's say self dot loss, and let's say append, and then I'm going to pass it here the self dot compute loss. Let's say compute loss, and inside that you can pass in here y comma predictions, because you have to pass in here the y true and the y predictions. And then after that, what I can do, we simply going to calculate the derivative for that. So let's say dw is equal to 1 divided by number of samples. Now the question is, in the linear regression using here the 2, but why in here 1? Why? See, it don't have any difference. You can using here, is it using here 2 either you can using here the one in like that. The difference is, see, if I using here the two or one two, so if we're going to calculate the same thing, the two should be crossed. I mean, we cutting here the one. That's mean in the same sector you need to using here, if you're using one or two, you can get in here the same exact value. You can cross it down to cross हो गया बस. So you can using here either one or either you can use the two. Same output you can got. Let's use here the one in the case of logistic regression, because in most of the cases in the Google they are still using here this one. Don't worry about that, because same thing बहुत, क्योंकि दो साइड में, दोनों साइड में दो है ना, तो काटा कट दो बस. काट आउट करने के बाद क्या मिलेगा, वन मिलेगा ना बस. सिंपल खत्म. Then after that we can using here this np dot dot, and then we are going to using here x dot transpose of that, so that we can also do the dot product of the x matrix to the our uh, x matrix to our predictions minus y matrix, I mean wx plus b matrix. So we can give it here predictions minus y. Let's say prediction minus y. So it should be predictions minus y. If I go to the slide again, then you can see we having those formula in the linear regression slide. I hope so. In here, you can see we need to do the xt, and that's our y prediction. That's called wx plus b, wx2 plus b, just like this. It's nothing but our dw. So what I can do, you can go on here, the code again. Here you go. Not here, actually, here. And then we're going to calculate the db. So it should be the 1 divided by number of samples, and you can using here the np dot sum, because bias is added. So let's say predictions minus y, and then after that what I can do, you can simply going to update the weight. Let's self dot weights is equal to self dot weights, okay, weights minus self dot learning rate into dw. This is the option formula, just mean weight is nothing but the new weight, and this is our world weight, and this is nothing but our learning rate into the dw. And then we have the self dot bias, and we can using here self dot bias. Let's say bias, we can using here the minus of self dot lr, that's mean learning rate, then you're using the db. Then after that we can using here the predict functions. So let's say def predict, and then you can passing here the self of x. Okay, it's quite time consuming to recording these two algorithm at a time. In the next one, actually posting here in the YouTube community box that I'm going to adding here 3 algorithm in one short video, but it's really taking time. And even though in the YouTube it's giving me some kind of time for uploading the videos, just like 3 days or 4 days, so it just make me inconsistent. So that's why I'm going to decide that I'm going to uploading here one single video about the one single machine learning algorithm, so that I can teach you in details. Okay, so now what I can do, I am simply going to do the prediction for that. Now in the case of logistic regression, we having an activation function called the sigmoid. In the sigmoid activation function, we having the minimum value is 0 and maximum value is 1. So now we need to giving here on threshold as well. If I see the graph of the sigmoid activation function, we having one threshold value, you can give it to here, it's up to you. Let's assume that 0.5 is nothing but my threshold value. If it is the value is greater than 0.5, we can simply going to making it as a 1. If it is less than 0.5, we can making it as a 0. This is we can you can do it here. I mean, you can setting here one threshold value, and this regression is called the logistic is used in the case of binary classification. You can do it using binary classification as well. So that's why the binary cross entropy is actually used in the form of calculating the errors. So you can go on here, and then I'm simply going to giving here a variable called threshold. So let's say threshold, and you can pass it here threshold, that's a 0.5. Then I'm going to calculate the y hat. Y hat is nothing but our y predictions. Y hat actually, not predicted actually. Y dot np dot dot. Now we have our actual weight and the biases. So let's our weights, because this weight is already calculated. It will keep updating the values in the form of gradient descent of the derivative. Then we having our weight and the biases. Then after that we can add in here self dot bias. Okay, and then we have the prediction. Let's say prediction predicted, and you can using here self dot sigmoid. sigmoid. Let's say sigmoid. Then what I can do, you can simply go to pass it here y hat, and then we can create here a class. Let's say y predicted class is equal to we can creating here one list comprehension, and you can say that let's say one if the I is greater than equal to threshold. That's a threshold. Okay, if it is one threshold, else you're going to making it as 0 for I in y predicted. Okay, if we got some kind of error for the variable declaration, we can replace it later on, no problem. It can be happen in the case of coding, because we are not a robot, right? So let's try to return here the np dot array, and we are going to passing here y predicted class, and then we're simply going to running this out. Let's say running this out. Okay, that's it. Now I can to use some examples use cases. That's x equal to np dot array. We're going to creating here one list of arrays. So let's clear 1 comma 0. Let's say uh, 0 comma 1. Let's say 0 comma 0, and then I'm going to using here, let's say 1 comma 1. So I'm going to give it here some kind of value. Let's say np dot array. This is nothing but our y matrices. So we can give it to, let's say 0 comma 0 comma 0 comma 1. That's mean if the all value is nothing but the 1, we can receive here a value called the 1. That's our actual output. Okay, so now we simply going to using here our model. So let's say model is equal to logistic regressions, and you can see it also give me suggestion. If you press the tab key from your keyboard, then you can using here model dot feed, and then you can using here this x comma y, and then you can use the prediction. Let's say prediction is equal to we can using here model dot predict. So model dot predict, you can passing here the x, and then you can printing it out. Let's say print here the prediction. Let's say prediction, and then you can passing here the prediction predictions, and you can using here the string. So let's see we got any error or not. So we got an error. Prediction is not defined. In the case of here, it should be predictions, right? Predictions. It can be happen. I already told you that, because we are not the robot. So again, we got an error. Epsilon is not defined. So if I see that the app, okay, it should be epsilon. Epsilon. It should be epsilon like that. Epsilon like that. Okay. So it should be here, and we have the epsilons. We have the epsilon just for the, yeah, okay. You can see here we got in here 0 0. All of the cases we got here 0, and we checking this out. You do any mistake or not, just for surety. Okay. So we give it here 1 plus 1 np dot exp of minus, and for calculating the loss, we getting here the epsilons, and you have the y true into np log y prediction plus epsilons. Then we have the 1 minus y true into np of log 1 minus y predictions plus epsilons, and you're going to be returning here minus np mean y1 plus y2. That's when all of the things is okay, fine. And in the case of iterations, we are going to using here uh, np dot product of that, and you're going to passing here inside one sigmoid activation function. We calculate the loss, we calculate the derivative of that, we calculate the biases, we're going to calculate update the weight, self weight minus learning into dwv. Okay, all of the things is okay. You can see here actually using here the same formula thing. Okay, so for I in y predicted. Cool. Now let's try to use it for one real world example, so that we can also clarify this one. It is really working or not, or is there any problem, so that we can solve it. Okay, because it's maybe the code error. So I'm simply going to write down one code quickly, and I'm going to pause the video because it's taking time. And here I'm going to using here some kind of technique or some kind of term that you are not discussing yet. So okay, I write down the code on here. Just for surety, we can checking it for the real-time data, because we see that we got in here all the value as a 0. This is not the convenient, right? So you can see here actually using the scikit-learn. See, using scikit-learn, you are not building here our model. That's our task to do that. See, if you are going to do building any kind of model, any kind of architecture in from the scratch, it will make your foundation strong in the case of machine learning, deep learning, or NLP, any kind of tasks. So that's why my motive is to make you perfect, make you strong, make your foundation strong in the case of AI. So that's why I recorded this video. That's why I'm creating this series. So you can see on here, we have scalar.model selection. You can using here the train toss split. What is this one? We are not discussing it here because we are not discussing it yet in the series. So how can we using here this one, or how can you using this data set? Okay, all of the things you're not discussing it here. Okay, just for the answer, I'm going to checking this one. You can using this train test split to split your data set into two part, training and the testing. Then you're going to using here the scikit-learn data set so that you can also load the data sets. So you have the load breast cancer. This is data set is available inside this data set in scikit-learn. Then you're going to divide them into the dependent and the independent features of the x and y. We have the dataset.data, we have the dataset.target. So that's means the target is nothing but called the y, and data or the feature column is called the x. Then we have this one. Okay, it's repeated second time, I hope so. Then we have our data, we're going to passing it inside one train, test, and split so that our model is not getting confused or our model is not getting overfitted in the case of non-linear data. So you have the x train, x test, y test, and then you're going to passing here inside this logistic regression that you created. You can passing here this learning rate of 0.003. You can using here this learning rate, low learning rate, and if you see on here, we're using here 0.01. Okay, so if I am going to using here this one, let's say I'm going to using here learning rate, let's say learning rate equal to 0.0001, and I'm going to using here number of iterations. Let's iteration equal to, let's say, 2000, and let's see what kind of value we got. You can got in here the same value, you can all see here. Okay, but in this case, let's try to running this out and see that what kind of output we got. And you can see here some output is 1, and some of the output is nothing but 0 that you can see on here. Okay, so if you can also checking this on your data set, you can checking here the x. You can see that how your data look like. Okay, because this is our data set data, you can also checking it like that. It's a data set dot data. You can also check in the value from like that. Okay, so if you have the target, it's nothing but our data. If I check in the target, I mean the y column that you can see on that, it having 0 0 0 0 like that. Okay, it will try to test the testing data. You can check in here the testing data. So you can check in the testing data, and you can see here you can also match it this out. You can matching this out, and you can also calculate the accuracy for that. So you're not going to calculate the accuracy or the FNS score or anything else, because of this is just nothing for coding from scratch or the machine learning algorithms. Okay, in the upcoming videos or in the series, I am trying to cover if all of the important topic called feature engineering, the outlier detections, or how can you calculate the accuracy, everything from scratch. So that's it for today now, and hope you enjoy this full tutorial, and make sure to subscribe to the channel and don't forget to hit the bell icon so that you'll get notified when I uploading in the next videos.